All right, everybody, we are going to continue with the 3.3 videos. So the next example wants us to write the equation of a tangent line for y equals 1/3 e to the x at the point x equals 0. So what we need in order to write the equation of the tangent line is we need the slope of the tangent line and we need a point for the tangent line. So when we do that, the slope of the tangent line is going to be the derivative of the function at that point. So the first thing we're going to do in this example is we are going to take the derivative of this function. So we're going to go y prime is equal to, we have a constant times a function. So the constant is 1/3, and then the derivative of e to the x is e to the x. From there, we're going to use that derivative to find the slope of the tangent line when x equals 0. So in this case, the slope of the tangent line is going to equal the derivative evaluated at 0, which in this case is going to be 1/3 e to the 0, and anything to the 0 power is 1, so we get 1/3. So now we have the slope of the tangent line being 1/3, which we found from the derivative. We also need a point. So we were not given a point, we were given an x coordinate. X was equal to 0. So we also need to figure out what is the y coordinate. So we're going to take y and evaluate it at 0, which is going to be 1/3 e to the 0, which is also 1/3. To write the equation of a tangent line, we can put it in either HK or point slope form. So if we put it in point slope form, it would be y minus 1/3 is equal to 1/3 times x minus 0. Now it's important that you understand where each of these 1/3s comes from. The slope of the tangent line, 1/3, is going here. The y coordinate of our point is going here. Now, some of you guys might prefer to write your answer in HK form, and that's perfectly fine. The only difference in HK form is instead of putting the y minus y1, you have a k over here, which is simply 1/3. Now, you also might notice that this could easily be put in slope-intercept form, which would be y equals 1/3 x plus 1/3. Now, any of those answers is going to be acceptable. It just really all depends on what you prefer. Most questions aren't going to tell you to write it in any one form. An equivalent form will get you the points. Next, we are going to talk about higher order derivatives. So everything we've looked at up to this point is the first derivative. And the first derivative is found the way we did it. There's also a second derivative. So second derivative might have the notation of y double prime, or it might be f double prime of x, or it might be d squared y dx squared, which is the second derivative of y with respect to x. You're doing that twice. There's a third derivative. So the third derivative could be y triple prime, f triple prime of x, and so forth. You know, you could do it as d cubed y over dx cubed. And again, it just kind of varies. Now, you could have an nth derivative. And the nth derivative, you know, would be y to the n basically, or f of n of x. Now, we don't typically deal with the nth derivative in this class. Most of the time, it's the first or the second derivative. It just depends. So, we have some examples below where we're given a function f of x, and we want to find the second derivative, and we want to find the third derivative. So f double prime of x, that's the second derivative. F with the little 3 there, that would be the third derivative of x. And in this case, f of x is given to us as negative 2x to the fifth minus 1 over x squared plus e to the x. The first thing I'm going to do in that problem is I'm going to rewrite that function so that I can apply our rules. So negative 2x to the fifth is fine. 1 over x squared, I'm going to rewrite that as x to the negative second power and then plus e to the x. And the reason we're doing that is we want to be able to apply those rules we talked about, power rules, things like that. So to find the second derivative, you really need the first derivative first. So we're going to use our sum and difference rules, our power rules, to find that first derivative. So the first derivative of f, if I apply the power rule to the first term, I'm going to multiply by 5. So that's going to be negative 10x. I'm going to reduce by 1, which is 4. Now, typically it's going to be minus. Now we're going to apply the power rule again, x to the negative second. We're going to multiply by negative 2, which makes this positive 2x. And you got to be careful here. You're reducing by 1. So negative 2 minus 1 is negative 3. And then plus the derivative of e to the x is e to the x. So that would be the first derivative, which we were not asked to find. But we need to find it in order to find the second derivative. The second derivative is simply the derivative of the first derivative. So the second derivative is equal to, apply the power rule to that first term. 4 times negative 10, that's going to be negative 40x to the third. I'm going to multiply, use the power rule again. So negative 3 times 2, that's going to be negative 6x. We're reducing by 1, so that's negative 4 plus e to the x. So that would be the second derivative. So the second derivative is this answer right here. We also are asked to find the third derivative. So the third derivative of x is going to be the derivative of the second derivative. So we take our second derivative, all right, apply the power rule for negative 40x cubed. So 3 times negative 40 is negative 120x squared. Apply the power rule for this middle term. We're going to multiply by negative 4, so that's positive 24x. Remember, we're reducing by 1, so that's negative 5 plus e to the x. And we can continue to do that as long as the derivatives exist. We could find a fourth derivative. We could find a fifth derivative, as long as those derivatives keep existing and don't just become 0. All right, I hope that helps you guys with higher order derivatives. Now, the next part of the notes, we're going to take a look at rates of change. So that's really what a derivative is. It is a rate of change. So if s of t represents the position of an object as a function of time, then the average velocity over a given time interval is simply the change in position over the change in time, which we have learned as slope. A lot of times we've talked about that as delta y over delta x. Here we're talking delta s over delta t, which is change in position over change in time. You know, you have that formula from algebra, y2 minus y1 over x2 minus x1. Those all apply. But when we're using slope between two specific points, we are finding the average velocity in that case. All right, which tells us the average rate of change between those 2 points. If we want to know the instantaneous velocity at a given point, that is where the derivative comes in. So the instantaneous velocity is the derivative of the function evaluated at a specific point in time. So that is going to be the end of part 2. There is going to be a third video for this lesson. So once you guys finish this, watch the third video, and that should complete the 3.3 notes for you.